In question number 7, two small electric dipoles of dipole moments P1 is equal to P and P2 is equal to 2P are located at separation L as shown in figure. The electric interaction energy between them is given by this expression. Find the value of N. So we know that the potential energy is given by U is equal to minus P dot E vector. So if I write the electric field at the location of P2, this can be further written as, that is equal to minus P, the value of P is P2, so P2 is 2P into electric field at the location of P2. So that can be written as 1 by 4 pi epsilon naught 2P cos theta upon R cube. So 1 upon 4 pi epsilon naught 2P. So 2 into value of P is P into cos 0 degree is 1 divided by R cube, that is L cube. So if I compare this with this expression, then the value of N comes out to be 4. So the correct answer for question number 7 is 04. Let's move to question number 8. In question number 8, a spherical shell of radius r with a uniform charge q has a point charge 2q at its center. The work performed by the electric forces during the cell expansion from radius r to 2r is given by this expression. Then we have to find out the value of N. So let it is a spherical shell of radius r and q charge is given to this spherical shell which is uniformly distributed, and 2q charge, point charge, is kept at the center of the shell. So if I write the initial energy, so if I write the initial electrostatic potential energy of this system, then it can be written as U initial is equal to self energy of spherical shell, that is half q square divided by 4 pi epsilon naught r, plus self energy of point charge is let U due to 2q, plus interaction energy between them can be written as charge into electric potential at the location of charge. So that can be written as 1 upon 4 pi epsilon naught into q by r. Now when the radius of the shell expands to 2r, then the final energy can be written as half into q square divided by 4 pi epsilon naught into 2r. The self energy of point charge will remain same into plus the interaction energy can be written as 2q into 1 divided by 4 pi epsilon naught q divided by 2r. So if I find out what is the work performed, that is equal to change in potential energy of the system. So if I solve this, that is U initial minus U final, then it comes out to be 5q square divided by 16 pi epsilon naught r. So on comparison, the value of N comes out to be 16. So the correct answer for question number 8 is 16. Let's move to question number 9. In question number 9, in the circuit shown, the switch S is at position 1 for a long time and then shifted to position 2. Find the amount of heat generated in the circuit. So if I check what is the initial charge on the capacitor of 100 microfarad, then on this capacitor this is positively charged and the charge would be Q C into V, that is 1000 micro Coulomb. So when the switch is shifted from 1 to 2, then the situation is something like this. The effective battery would be this. So this would be 10 volt. Now this plate is positively charged and the total charge on the capacitor in this situation is again 1000 micro Coulomb. So if I write the work done by battery, that is equal to U final minus U initial plus heat loss. So we can see that U initial and U final are same, so they would cancel out. So the heat loss is equal to work done by battery, so that is charge flown through battery into potential difference of battery. So we can say that the charge flown through battery is equal to, if I see the charge on this plate, initially the charge on this plate is minus of 1000 microcoulomb and now it is plus 1000 microcoulomb. So the change is of 2000 microcoulomb or 2 millicoulomb. So we can write 2 millicoulomb into the EMF of battery is 10 volt. So on further solving, this can be written as 20 millijoule. So the correct answer for question number 9 is 20. Let's move to question number 10. In question number 10, 4 large conducting plates are arranged parallel and 3 of them given charges as shown. If one of the plate is earthed by pressing switch S, then find the charge in microcoulomb appeared on the surface 4. So we know that when one of the plate is earthed, then the charge on the outer surface of the outer plates must be 0. So in that situation, the charge on this plate is 0 as well as the charge on this plate is 0. So if 0 is the charge on this plate, then minus 30 would be the charge on this plate and the total charge on this isolated plate is minus 30 microcoulomb. So if it is minus 30, then this would be plus 30, and if it is plus 30, then the total charge on this plate is 80 microcoulomb. So the charge on this plate is plus 50 microcoulomb. So we can see that the charge on the plate 4 in this situation is plus 50. Similarly, if I proceed further, then the charge on this plate is minus 50, and since the charge on this plate is plus 20, so the charge here would be plus 20, on this side is minus 20. So in this situation, we can say that the charge appeared on the surface 4 is plus 50 microcoulomb. So the correct answer for question number 10 is 50. Let's move to question number 11. In question number 11, 2 short electric dipoles, each of dipole moment P, are placed at large separation D with their axis coinciding. The electric force of interaction between them is given by this expression. So we have to find the value of N. So in the question it is given that, suppose this is one of the short dipole and another it is short dipole. Their dipole moment is P, and it is given that, I am assuming that the separation between them is X. So the interaction potential energy between the dipoles is given by U is equal to minus of P into P dot E. So that can be written as P into E can be written as 1 divided by 4 pi epsilon naught into 2P cos theta. So that is 2 into P, cos theta value is 1, divided by X cube. 2P cos theta divided by R cube. Now we have to find out the electric force of interaction between them. So that can be written as minus of du by dx. So if I differentiate this, so this comes out to be 2p square divided by 4 pi epsilon naught into differentiation of 1 by x cube can be written as minus 3 divided by x raised to the power 4. So if I find out the electric force of interaction between them when the separation them becomes D, then F can be written as 12 p square divided by 8 pi epsilon naught into D raised to the power 4. So on comparison, the value of N comes out to be 12. So the correct answer for question number 11 is 12. Let's move to question number 12. In question number 12, a capacitor A of 1 microfarad is charged to a potential difference of 110 volt and then connected to a circuit as shown. Switch S is then closed. Capacitor B and C were initially uncharged. Find the charge flown through the switch in microcoulomb. So initially the charge on this capacitor is 110 microcoulomb. Let the X amount of charge has flown through this capacitor. Then the charge on this plate would be X, on this plate would be X, and similarly the charge on this plate would be minus 110 plus X, because X charge come to this plate. So if I apply the KVL, then the net potential difference in the loop must be 0. So we can write the equation in this way. I am moving from here in this direction. then x divided by 2 plus x divided by 3 plus minus 110 plus x divided by 1 must be equal to 0. So if I solve this, the value of x comes out to be 60 microcoulomb. So the correct answer for question number 12 is 60. Let's move to question number 13. In question number 13, a line of electric field created by 2 point charges Q1 and Q2 is shown in the figure. If Q1 is equal to this, then find the value of Q2. So we know that Q1 charge is negative. So if I consider at this point, then at this point the electric field due to Q1 charge is in this direction, and let it is E1. Since we can see here the direction of electric field lines at this point is horizontal, so the net electric field along the vertical line must be 0. So if E1 is in this direction, then E2 at this point due to charge Q2 must be in this direction, because if E2 also comes in this direction towards Q2, then the net electric field would not be horizontal. So if E2 is this, then we can say that let this angle is θ1 and then this angle is θ2, then the net electric field would be horizontal due to E1 and E2. So if I see, the vertical component of E1 and E2 must be balanced. So this angle is θ1 and this angle would be θ2. So E1 sin θ1 must be equal to E2 sin θ2. So now we can substitute the value. The value of E1 is K into Q1 divided by R square. So we can see here, if I consider this as my 1 unit, then this would be 1, 2, 3 and here it is 6. So it would be 6 square plus 3 unit square. So that is R square into sin θ1. So that is perpendicular upon hypotenuse. So perpendicular would be 3 divided by hypotenuse would be under root of 6 square plus 3 square, and that must be equal to K into Q2 divided by R square. So R square would be 3 square plus 3 square, because this unit will be 3 and this unit is also 3, into sin θ2. So that is perpendicular 3 divided by under root of 3 square plus 3 square. So if I substitute the value of Q1 and solve for Q2, then the value of Q2 comes out to be 80 microcoulomb. So the correct answer for question number 13 is 80. Let's move to question number 14. In question number 14, a non-conducting square plate of side A is uniformly charged with Q, and a particle of charge Q is placed at a distance a by 2 from the plate on an axis passing through the center of plate and perpendicular to it as shown. The electric force on the particle due to the charge on the plate is given by this expression. So we have to find out the value of N. So let's analyze the situation. Suppose this is a plate on which Q charge is uniformly distributed, and this is the location of the point charge Q. Now suppose the surface charge density of this plate is sigma, so that can be written as Q divided by A square, charge per unit area. Suppose I am considering an element dA, then the electric field at this location would be in this direction, electric field. So let the charge on this is dq, then the dq would be sigma into d. So the df on this element can be written as df is equal to charge, that is sigma into dA, into the electric field at the location of this charge due to point charge. So that would be the direction of electric field is in this direction at this location into E. So if I take the component of this force perpendicular to the plate and parallel to the plate then due to symmetry, the net force would come in the perpendicular direction. Because if I consider another element at this situation, then the force would be in this direction. Then if I take the component, one component is this and the other component is parallel to the plate, so due to symmetry, the net force would come in the perpendicular direction. So F net can be written as integration of dF perpendicular component, and this perpendicular component dF perpendicular would be, if area vector of this element is in this direction, then this angle is theta, then this can be written as dF cos theta. So on substituting dF cos theta, so it comes out to be sigma into dA into E into cos theta. So we can see that if I integrate E dA cos theta, because sigma is constant, it comes out of the integration, then this value E dA cos theta would give the flux passing through this non-conducting square plate due to charge Q. So sigma into phi, and we know that through this square plate the flux passing through due to charge Q is Q by epsilon naught divided by 6. So if I substitute the value of sigma, then it comes out to be 2 capital Q small q divided by 12 epsilon naught a square. So on comparison, the value of n comes out to be 12. Let's move to the first paragraph containing question number 15 and 16.